we are continuing Module 1, What is this thing called weather? And today we are covering precipitation. So just a quick little quote for you that I thought I'd share. The typical cumulus cloud, I have a picture of a cumulonimbus here. If you assume it's a kilometer across, a kilometer long, and a kilometer tall, then we get a cube, right? Like a little three-dimensional square. And so that's 1 billion cubic meters in volume. And then if you do some math, it roughly weighs 1.1 million pounds. And just to give you a figure of like, how much does a cloud weigh? And if you don't know how much that is roughly 100 elephants. So I have some elephants here for you. So elephants equal cloud. So how does it stay up there? Well, remember that water vapor is less dense than air, so that's one reason. So the density of it, and then also the fact that there's wind that's keeping up those little water droplets. So just thought I'd share that with you to start with. So how does precipitation form? That is our mission today. So we have condensation nuclei, that's what we covered last class, forming our clouds. They are the little specks here. They are roughly 0.0002 millimeters across. And then as we condense our water vapor onto those surfaces, we will form the typical cloud droplet, which is 0.02 millimeters, which is approximately 1, 2, or 100 times larger. I was just moving the decimal point for you. And then if I put two of those together, double in size, that's a large cloud droplet. So then where's the rain droplet? Oh yeah, it's this big giant sphere at the bottom. So the typical rain droplet is 2 millimeters in diameter. So it is huge compared to our condensation nuclei, our cloud droplets, and even a typical human hair. Not mine. Mine is thicker than that. Anyways. Okay, so we have two processes how precipitation forms. I will start with warm clouds. So in warm clouds, we have something called the collision-coalescence process. So this is the dominant process in warm clouds. It's by multiple collisions of tiny cloud droplets that stick together or coalesce to form rain droplets large enough to reach the ground before evaporating. I have the cloud droplet size and fall velocities to your right. So small cloud droplets have a diameter of 0.01 millimeters and fall at roughly 0.006 miles per hour. That's really, really slow. Now, as we move to a large cloud droplet size, it's 0.05 millimeters across and it moves at 0.2 miles per hour. But as we get to typical rain droplets, they can move up to 14 miles per hour. That's what it hurts when it hits your face, right? And then large rain droplets, can fall at about 20 miles per hour. So the way I explain this is, let's say you are on the beltway and you're driving your car, right? And as you're driving your car, someone cuts you off, because that never happens, right? And as they cut you off, they bump your car, and instead of your car bumping off and like skidding off in a different direction, instead, your two cars then coalesce together and become one car. That's what I'm talking about. So the two cars being the cloud droplets, and then the coalescing being that collision-coalescence process. So here is it in our little cloud situation. So we have copious amount of rainfall associated with clouds below the freezing level. These are called warm clouds, especially in the tropics. And our smaller droplets hit other droplets to become larger, and as they collide with more droplets, their fall velocity increases. So here's our typical cloud droplets here, little dots. They form together and we get a large cloud droplet of 0.05 millimeters, again double in size roughly speaking. And then as it falls, it becomes like a pancake, and all of the other cloud droplets stick to the bottom of it. They can't get out of the way. So then this one gets bigger. You see here, now we have a very giant pancake that's flying, and that one collision coalesces even more droplets, and then eventually they might shear apart and begin the whole process again. So depending on how many get in the way. So that is collision coalescence. So now The other process is called the Bergeron process. This is for cold clouds. Sorry. So first thing you need to note is super cold water. So this is water in the liquid state that is below 32 degrees Fahrenheit or 0 degrees C. Sorry. And so this water is literally liquid and it's below freezing. So yes, it happens. And if the droplets are microscopic, they can actually stay in liquid form as low as 40 degrees below zero. And that's both Fahrenheit and Celsius because the two are equal at this point. But that's only for pure water, which only exists in laboratory conditions, which we know is not the atmosphere. So, just to review from the last lesson, in order to form clouds, we have to have condensation nuclei. These are our tiny particles that serve as surfaces for water vapor to condense onto. We have the two types, hygroscopic, which is water-seeking, like salt, and then hydrophobic, like oil, and that is water-repelling. As the cloud grows, it is rapid at first, but then it slows as the water vapor is consumed. It results in the formation of our cloud, which consists of billions of tiny water droplets, which makes it really easy to form our precipitation, right? Because we have lots of moisture present. So, thanks to those suspended particles, I want to make sure I said that right, or condensation nuclei, as we call it in our textbook, the temperature at which our liquid droplets freeze is closer to 12 below Celsius or 10 degrees Fahrenheit, which is much more attainable at our cloud elevations. Remember, clouds form above the surface, so the temperature is going to be colder at those altitudes than if it was at the surface. So if we didn't have any condensation nuclei in a crystal clear, pure atmosphere, it would never rain. So we definitely need our condensation nuclei. Good thing we have tons of those around, right? So when it comes to the Bergeron process, we know that the saturation vapor pressure over ice crystals is actually lower than it is over water droplets. So the relative humidity is 100% with respect to water droplets, but with respect to ice, it's 110%. Like, what? What does that mean? Well, it means that the water vapor thinks that the relative humidity is higher when there's ice than when there's water droplets. So it thinks that it's higher than if there's water droplets. And ice crystals are solid, so it holds those molecules closely together. Remember our hydrogen bonds from last time, so they're holding really tightly together. So for that reason, we have the water vapor molecules escaping from our water droplets at a faster rate than from our ice crystals. So to recap, the ice crystals have that hexagonal, I don't know what that was, that hexagonal hydrogen bond crystalline pattern, so it can like hold really tightly together. So basically it's harder for the water vapor to escape from that. So it escapes from our water vapor molecules onto the ice crystals. So I'll show you right here. Here's a picture. So I like to call this the vampire process. I should copyright that, but anyway. So here's our ice crystal. These are our little Mickey Mouses, again, not a sponsor. They are water molecules, and these are our cloud droplets. So all the water molecules are changing or escaping from the cloud droplets and moving onto the ice crystal, okay? So the ice crystal grows at the expense of the cloud droplets. That's what the Bergeron process says. Ice crystals grow at the expense of cloud droplets until they're large enough to fall. So our cloud has to have three things. One, water vapor, duh. It has to have liquid cloud droplets, and it has to have ice crystals. So once I have my ice crystal, the water molecules will then form onto it. So it's speeding, I don't know if you can see, but it's speeding away from the cloud droplet towards the ice crystal. Ice crystal gets bigger, cloud droplets get smaller. So as more speed over towards the ice crystal gets bigger, the cloud droplets get smaller until these disappear. Snow crystal is now big enough to fall, and it falls to the earth. That's the Bergeron process. Again, it grows at the expense of the cloud droplets. So the cloud droplets gets the light sucked out of them, just like vampires, and the snow crystal gets bigger, right? So ice crystal and then snow crystal when it's big enough to fall. As opposed to the warm cloud process where they just smash together and then they become bigger and bigger and then they fall. Okay, so one's kind of like sucking the life out of the cloud droplets, the other one is smashing into them. Okay, so these are our types of precipitation. This is a table if you need a description or to find out is it liquid or solid, what size it is, etc. So the first forms of precipitation we're going to start with are from warm clouds. So rain, which is restricted to droplets of water with a diameter of at least 0.5 millimeters, looks kind of like this on your windshield. Then cloudbursts, which are unusually heavy rainfalls. Here you see one that I was chasing. I think that was a cloud of snow there, perhaps. Drizzle, which is uniform fine droplets with a diameter less than 0.5 millimeters. This is the stuff that gets on your windshield. You turn on your windshield wipers and it goes right like that because it's too small. There's not enough water yet for the wipers to work. Then there's virga, which can be rain or snow, which evaporates above the ground. It looks kind of like this. So there's a layer of dry air here. It's evaporating through. And then mist, kind of like Pluto in astronomy, was decommissioned as a form of precipitation. I still include it. It contains the smallest droplets. It looks like fog mist. It's kind of the same thing. So when you walk through fog, you notice you get moisture in your clothing. That's mist. So I have examples that we go through in class. I'm not going to view them here for copyright purposes. So we have like the sleep sounds where they record it for like 10 hours or more. So there's heavy rain here on the left, then there's light rain on the right, and then there's what is a cloudburst from an Indian meteorology community. Okay, so forms of precipitation, we have cold now. So we have snow. This is precipitation in the form of ice crystals or aggregate of ice crystals. You can see in the top right a dendrite. That's a type of ice crystal that is snow. And then when they get together in a big clump, it's called an aggregate. That's what they kind of look like in Maryland. They kind of fall as a big lump. But there's still little individual ice crystals you can see inside of them. Then there's graupel. This is when a snowflake collects super cool water droplets on its surface. Not to be confused with sleet, which I'll get to in a minute. Graupel is white in color, and it kind of looks like Dippin' Dots, I guess. Kind of just like little puffs, or really tiny cotton balls. I don't know. That's what they look like to me. Anyway, so the snowflake gets covered with super cool droplets of water, and then it becomes white, falls to the ground. Some people call it soft hail. It's not really hail. It's called graupel for a reason, because it's something else. Okay, so who was the first person to study snow? That would be the 16th century Swedish historian Olaus Magnus. He was the first to study individual snow crystals. There's one right there. He's so cute. And then his contemporary was mathematicians Descartes and Kepler, who are French and German respectively. And then a little later in the 20th century, we had William Bentley and his catalog of snowflake forms. This was a farmer in America who from age 20 to 60 built a collection of 6,000 photographs of snowflakes, and he found that there was an infinite variety of crystal shapes that existed. This is just one example from this website, so if you go there, you can check out. It's totally devoted to his study of the snowflake forms. So something that we discovered, probably because of his research, is that higher humidity or colder temperatures lead to different snow crystal shapes. So I had to study this diagram in school. You don't need to know this, but this is just for fun. So the colder the temperature gives you different sized ice crystals. So we see plates, columns, more plates, even more plates and columns. but then the higher the humidity, the larger it gets, right? So we have a very large den right here, which is in the plates, and I've seen needles in person. So our cloud professor used to tell us to stick out your arm, which you'd have your coat on, and it has that waterproof seal on it, so you'd be able to catch snowflakes and then study them and identify what type of ice crystal it was. He was kind of goofy, but anyway, so dendrites are very popular. These are, again, you need like colder cloud temperatures for this and lower humidity, so it's going to be smaller. But anyway, so different ice crystal shapes. Now here's a question: can it ever be too cold for snow? The answer is kind of. So if the air is very cold, the water vapor content is quite low. Remember our humidity discussion last lesson. So smaller bucket size, smaller amount of humidity available. So cold air delivers less precipitation because it's dry. But it can still never really be too cold to snow because there's still going to be like some small fraction of water vapor present. So the coldest place in the world is the South Pole. It gets about 10 to 20 inches of snow each year, but it's technically a desert. That might be surprising to you. The snow never melts. So it looks like that. That's a real place. That's Antarctica. Most northern U.S. cities receive 3 times as much snow as the South Pole. Hence, it's a desert, right? But our snow melts up here as opposed to the South Pole where it just keeps piling up deeper and deeper and deeper. All right, so if you were in class, you would watch the time lapse of this Colorado snowstorm, which I found from March 2021. And then this is a video about graupel, which I found was very helpful. Okay, so moving to more frozen precipitation, we have sleet and freezing rain. These are the most confused 2 types of frozen precipitation, I think, out of the lot of them. So sleet is translucent. It's about the same size as graupel, but it's translucent. It's clear. So this is rain droplets that freeze while falling. So it's a frozen raindrop that then hits the surface. Freezing rain is rain droplets that are super cooled, then it hits the surface, then it freezes. Okay, so again, freezing while falling is sleet. Freezing on contact is freezing rain, or glaze. It's also called glaze. So on the left, you see the picture of my old car, rest in pieces, and this was a sleet storm that came through while I was teaching. So this is at Rockville, and there was like a little light coating of sleet on my car when I came out. That was kind of interesting. So I took a picture for you. And then this is from the Great Ice Storm of 1998 in Toronto, Canada. Or is it Ontario? Anyways, it's up north, and you can see like everything is coated. Even the stop sign got little drippy bits there. So everything is just coated completely with freezing rain. Now, you might find that in Maryland we use the term wintry mix. That's because you can kind of get a little bit of everything. It can sleet, freezing rain, and snow at the same time here. So yeah, that's totally a thing. So this is why we have a temperature profile. For rain here, the cloud is in the cold zone. I'll just say cold zone, below 0, right? So it's snowing up here at cloud level. Then as it passes into the melt zone, or the warmer area towards the surface, it turns into rain. That is rain. Snow is also pretty easy. We have at cloud level, it's below 0, it's cold. And then at the ground, it's cold. Now you can still get snow a little bit above 0, maybe up to like 40-ish degrees Fahrenheit. But generally speaking, it's just going to be below 0 snow. Now, the 2 complicated ones. Sleet. Sleet, I have snow up here, and then it passes through this area where it melts, and then refreezes. Remember, the raindrop freezes, and then it hits the ground as sleet. As opposed to glaze or freezing rain, where it starts as snow, it melts, and then there's a teeny little shallow layer at the surface where it freezes on contact. Okay, so again, deeper layer of cold makes it freeze before the surface. Shallow layer means that it's freezing on contact. So next we will watch a video about a sleet storm. This is from Missouri or the Midwest somewhere. And you can see the little pellets kind of bouncing off the surface. That's how you can tell it's sleet. As opposed to this freezing rain video where this guy literally is like crunching his car door open and like smashing out the glaze by his driver's side window. This one's really fun to watch. Probably not good for his car, but fun to watch nonetheless. Okay, so then we have hail. Hail is a precipitation in the form of hard, round pellets of ice. It is produced in cumulonimbus clouds, that is thunderstorm clouds. Hailstones begin as tiny ice pellets. They actually start as graupel, and they grow as they're propelled by updrafts and downdrafts through the cloud. They vary in sizes. Obviously, this can cause quite a bit of damage to vehicles, specifically windshields. I believe this one is a record breaker, and I think it's about 8 inches across. And then this one is the one in the textbook. You can see the youngest part of the hail is in the middle. Literally, you can see the ice pellet there. And then the super cooled water on the outside of that. This is some pea-sized hail that was in a friend's backyard in Silver Spring. So I picked up some, I took a picture. That is my hand. It was kind of a freak storm. It was very interesting to just kind of like, oh, there's hail right now. And then we have rime. By the way, hail is a warm cloud precipitation, not a cold cloud. So rime is a deposit of ice crystals formed on surface objects by supercooled fog or cloud droplets. It occurs when the surface temperature of an object is below freezing. So we have the surface temperature of this object, which is a leaf, and it's below freezing, and then the supercooled fog passes by and it freezes on the outside of the leaf. So I show you these two videos where there's a hailstorm in Oklahoma City, and they say they're about baseball size, but they look more like golf ball size to me. But they were talking about how their car is like completely destroyed, and there are a lot of insurance claims for it. And there's actually something called hail shutters that you put on your vehicle in areas where there are hailstorms quite frequently. Plus, I have a video here of a helicopter that nearly crashed due to icing. So they passed through a supercooled fog, and there's riming on the edge of the propellers. They're not able to get lift. So you can watch that at your leisure. So what's your favorite type of precipitation? I have a lot of people who are snow lovers. I like snow in decent amounts, but I don't really care for blizzards personally because I'm the shoveler. Anyway, okay, so last up we have weather modification. So just talking about rain and snow making. There's the traditional First Nation rain dances. I think almost everybody has heard of these. They're in movies, etc., etc., but based on real, actual traditions. And then in the early 1940s, Vincent Schaefer tried to produce more ice crystals in clouds by tossing, get this, dry ice out of airplanes. So that didn't work. It just kind of fell to the ground, which is like problematic. It's just like falling through people's houses. That is solid carbon dioxide, by the way. However, then he broke it into small pieces, which did sort of work. But then Bernard van Gogh, I guess is his name, found that the chemical silver iodine has crystal faces like real ice. It can be injected from the ground level or from planes, and it has this attractive property for the water vapor to form onto it. So however, if it's exposed to sunlight, it loses that attractive property. So experiments have been continuing from the 50s to the 70s. It had hit or miss results, nothing really consistent showing that we could make rain or snow, although there are still companies who claim to be weather control, and people pay for it. I'm just saying. So here's cloud seeding. It's a process that introduces silver iodine or dry ice into a cloud for producing rain. It's also been attempted for hail, but sometimes it generated bigger hail or more hail, so that's kind of bad. And then when they tried to seed hurricanes, it had similar results. Worse hurricanes, more rain. So cut that out. More than half the states in the United States have laws controlling weather controllers for that reason, because it's kind of not sure if it works or not. So here's just kind of the process on the right. You have the silver iodine being released, either it's from the ground or from the cloud. It goes in from the cloud, from the plane into the cloud, and then the cloud aids, gets that aid from the silver iodine to make ice crystals, and then it's supposed to fall out as snow or rain, depending on the temperature. Okay. Also, fog or stratus dispersal. This is important when it comes to aircraft. Not sure why I have agriculture here, but aircraft. So you can do one of three things. So the first one is wait for the sun to heat the environment above the saturation temperature, or the dew point, which is why people call it like fog burning off. It's not technically true, but that's how people think of it. Or you could simulate mixing, right? Get a big fan, do something like that to mix out the fog. Or we can spread particles of dry ice into the layer of cloud to disperse them. You see an experiment here done in the black and white photo era. I don't have the exact date on this photo, but you can see it made a hole in the cloud, so it works. Then there's hail suppression. So in an attempt to control hail in 1896, Albert Stinger, an Austrian wind grower, invented a hail cannon, which was a cast iron mortar. It had a metal smokestack, which was attached to a muzzle to act as a sound box, which would increase noise even more. This apparatus became very popular around the world. In 1900, there were 7,000 in Italy alone, but it caused 11 deaths and 60 serious injuries to these hail explosions. So by the end of use in 1902, it was discredited by the Italian and Austrian governments. So yeah, that didn't work out for him. Oh, that's what it looks like, right? So we have like shooting things into the cloud. Finally, for planned weather modification, we have frost prevention. So if you don't know, oranges or citrus fruits are pretty sensitive to temperature. So if they freeze, your crop is ruined. So you need to have a way to prevent frost or freezing from happening. There are two ways. One is mechanical. I get a wind machine, looks like that in real life, and it mixes the different layers, so I keep the temperature at the surface, right? Instead of over here being below freezing, we keep it above freezing, or nearly, right? The other way is to burn stuff. So I get a little furnace, right? I burn some things. There it is in the orchard there. There's the baby oranges, right? They haven't grown yet. So it produces this heat going outward and upward. So it also causes mixing, which keeps it above freezing. So either way, we're preventing frost from happening, which keeps our orchard happy. Yay! So I hope you enjoyed this talk about precipitation. See you next time.